Hi everyone, welcome back to the channel. Today we are going to walk through the system design of YouTube, one of the most traffic-heavy globally distributed system ever built. We are going to break it down into multiple parts. First, functional requirements, then non-functional requirements. We will also discuss about the APIs that tie everything together. Then we will discuss about high-level design and deep dive. So, let's get started. Let's talk about what our system must do. These are the functional requirements. First, upload videos. Users should be able to upload videos from anywhere in the world. Uploads needs to be resumable, fault-tolerant, and should allow large files, sometimes several gigabytes. Once the raw video is uploaded, the system should store it, trigger transcoding into multiple formats like 144p, 720p, and 4K, and then generate thumbnails and metadata. Now, second functional requirement is search videos. Users must be able to search videos by title, keywords, and descriptions. Search results must be fast and relevant, even if the query is misspelled or partially typed. Third, stream videos. Users should be able to stream videos seamlessly. This means adaptive bitrate streaming, CDN caching, and delivering content in small chunks through HLS or Dash protocols. The system should ensure minimum buffering and smooth playback. So, those are the core functional requirements: upload, search, and stream. Now let's switch gears and look into non-functional requirements, the backbone of a system at YouTube scale. So, first, high availability. YouTube must be available 24/7 across all continents. Essential services like search, streaming, and playback should have extremely high uptime. Second, scalability. The system has to scale horizontally to handle billions of daily views, millions of uploads, and massive global search traffic. This means microservices, distributed storage, sharded database, and auto-scaling. Third, low latency or low bandwidth. Users expect fast search results and instant playback. You must optimize bandwidth usage and rely heavily on CDNs to serve videos, content from locations closest to the user. Fourth, eventual consistency. Now here, sometimes like when you ask or when you're discussing about non-functional requirement, if you're a beginner, it's okay if you don't mention about strong consistency versus eventual consistency, but if you're an advanced or senior engineer, it would be great if you mention about eventual consistency during non-functional requirement. Now, why eventual consistency but not strong consistency? The reason is some parts of the system like search, indexing, and recommendation updates can be eventual consistent. So, as an example, after you upload a video, it may take a few seconds to appear in search results, and that's acceptable, it's okay. Now, next, which is the last non-functional requirement which we are going to focus in this video, is redundancy and fault tolerance. We replicate data across regions, have redundant storage, and ensure that even if a whole region goes down, our system continues operating smoothly. So these are the functional and non-functional requirements which we are going to discuss in today's video. Now let's discuss about back-of-the-envelope estimation. Let's assume this product has 5 million daily active users, and each user watches 5 videos per day. And out of those users, 10% of users upload 1 video per day. And also let's assume that average size of the video is 300 MB. In this case, total daily storage space needed is equals to 5 million into 10% of users into 300 MB equals to 150 terabyte. So basically we need a huge storage space, 150 terabyte of space. And let's discuss about APIs next. So in APIs, basically we have 3 core functional requirements: upload videos, search videos, and stream videos. We are going to create different API for each of this functional requirement. Our first API is upload API. So in upload API, basically when we are uploading a video, there are chances that some videos are short video and some are really large video. When we are uploading a large video, we don't want to upload that large video just in one go. We would like to upload that large video in smaller chunks. So for large video, we need to pass the resumable parameter equals to true. So in this case, that's how the upload API knows that we are uploading this video in smaller chunks. So the request parameter for this API is video title, chunk number, total chunks, and data. And the response parameter is the status, the video ID, and the message. So this is how our upload API will work. The second API is search API. In search API, we are going to pass the parameter as title equals to XYZ. Basically, whenever user is typing something in search bar, we are going to pass this in a search query. and the response will contain multiple videos results. It might be 1, it might be 100, it might be 10 based on the number matching numbers. So in the response, we will have array of results which will include video ID, title, description, and thumbnail URL. So by doing this, we can just display the basic results in the search area. So this is how our search API will return results. Now the third API is basically stream API. When user is trying to stream a video, basically from search results they will pick one video which they like it, and when they try to stream, they try to play the video, we will pass video ID into string parameter, and in response we will return the manifest URL. And this is how our API will be defined. Now let's start with high-level design. In high-level design, we are going to focus on the major components for the system design for YouTube. First, we will start with upload videos. So basically, upload video starts with the user. When user comes to the system, they will upload video, and our request will go from user to API gateway. API gateway basically it helps us in terms of power routing this request to the API servers, as well as we can also use API gateway for multiple other features like rate limiting and throttling. We can also use it for authentication and authorization. So the request will go from user to API gateway and API gateway to upload API. Upload API service will basically upload metadata related to this video into the metadata database, and as well as it will also update the metadata cache. So in metadata database, we will have some of the features which is like video title, video description, etc. in database. Once we have metadata in the database, upload API will send a request to S3 to get pre-signed URLs. And once we have pre-signed URLs, upload API will send those pre-signed URLs back to user. Once user has pre-signed URL, then they can upload the raw video directly to S3. And this is how our upload video will work. We will go in deep dive later on in this video in terms of the actual how do we make the video shorter, etc. I mean, how do we make the video, how do we upload video in the small chunks? Now, once we have raw video in S3, we will pass this video to transcoding servers. Why do we need transcoding? Basically, each device has different kind of format needed. So when you are accessing any video from laptop versus mobile versus any other devices, we need to use a different format based on the device, and transcoding servers will transcode each video into different formats. And once the transcoding is complete, then it will store transcoded data back into S3. So basically, again, we will have all transcoded videos into S3. And on the other side, once transcode is completed, it will send status of transcode complete into message queue. And then message queue will basically send the status update to metadata database. And this is how the metadata database will know that the transcoding is complete for that particular video. So this is how our upload API flow works. Now let's look into the second flow, which is basically search API. So when user searches any video, the request will again go from user to API gateway, and API gateway will route the request to search API servers. Once search API gets any request to search any data, it will send a request to metadata cache. And for any reason, if cache doesn't have data for the particular search, then it will search directly to metadata database. And once it gets the results, the search API will send the JSON response to user. So this is our second request in terms of search API. And our third functional requirement is basically stream video. So for stream video, we will use stream API. Again, the request will go from user to API gateway and API gateway to stream API. Here, stream API will get the video from CDN. And if the particular video is not available in CDN, then the request will go through S3, and stream API will get the video and will display the video to user. So this is very high level in terms of how video upload, search, and stream will work. Alright, let's deep dive into one of the most complex and fascinating parts of a YouTube-like system, the video transcoding pipeline. Whenever a user uploads a video, we don't treat it as a one big file. It actually contains three separate components: video, audio, and metadata. So basically, original video is broken down in three parts: video, audio, and metadata. Now, let's focus first on the video track. When we split out the video portion, several tasks run, like inspection, transcoding, thumbnail, inspection, etc. Inspection basically was the codec, resolution, frame rate, video transcoding, converting the original video into different formats like 1080p, 720p, 480p, etc. Thumbnail generation, extracting keyframes for previews, watermarking if the platform needs branded content, and extras like sync detection or GIF previews. Then there is an audio track. Audio track has its own separate pipeline. It will do audio extraction and audio encoding into formats like AAC or OPUs, and loudness normalization. And the final track, which is metadata, that is extracted and stored as is it. So the flow looks like original video to video track to multiple task, task to assemble, then video, original video to audio track to audio recording, audio encoding, assemble, and from original video to metadata to assemble. Everything eventually comes back together during the packaging stage. Now, let's get into the actual transcoding system architecture, which is the engine behind everything. This is where things get interesting. We typically use a pipeline like preprocessor to DAG scheduler, to resource manager, task workers, and encoded video. Now, first, let's look into preprocessor. This is the first major component. It reads the original video, it accesses video and audio tracks, identifies all required outputs like 1080p, 720p, thumbnails, etc. It generates a DAG or directed acyclic graph describing all tasks. It stores intermediate data into temporary storage. Think of the preprocessor as creating a to-do list with dependencies. First inspect the video, then start 1080p and 720p encoding, then generate thumbnails after scene detection, and so on. Now, next comes DAG scheduler. It's job to walk through the dependency graph and ask, what task is ready to run now? Which task depends on others? Which task can run in parallel? For example, 1080p encoding can start only after inspection. Thumbnail extraction may need keyframe info. Audio encoding can run immediately if audio is extracted. If you're watching this, think for a second. How many tasks do you think are involved in processing a single 10-minute YouTube video? Dozens, sometimes hundreds. Now, we send runnable tasks to the resource manager. This component decides which worker should handle which task. Whether a task needs a GPU or CPU, how many workers to allocate, how to scale up or down based on load, how to prioritize urgent or popular uploads. This is similar to Kubernetes but specialized for media processing. Then task workers. Task workers are the ones doing the actual work. GPU workers handle 4K or 8K or AV1 encores. CPU workers handle thumbnails, watermarks, and light tasks. Each worker picks a task, processes it, and writes the results to temporary storage. The preprocessor and workers keep reading or writing intermediate data until every node in the DAG is complete. This design allows massive parallelism. A single high-resolution video might be split across 10 workers for different resolutions. 3 workers for thumbnails, 1 worker for inspection, 1 worker for audio encoding, all running in parallel. And now last one, which is final assembly. Once all video tasks and audio tasks are complete, the system merges video and audio streams. It packages them into HLS or dash formats. It turns different manifest. It uploads everything to permanent storage. And finally, marks the video as ready to stream. This is the moment the video becomes playable from the CDN. So to recap, we break the video into video, audio, and metadata. The video batch runs tasks like inspection, transcoding, thumbnails, watermarking. The audio branch runs its own encoding task. A preprocessor builds a DAG for all work. A scheduler and resource manager orchestrate everything. Worker processes task and writes to temporary storage. Final assembly merges everything into streaming formats. This pipeline allows platforms like YouTube to handle millions of uploads per day at scale with reliability and parallelism built into every stage. Well, we just completed transcoding and now let's go with our next deep dive, which is video streaming. This is the part users care about the most. Can I hit play and watch instantly without buffering? So let's start with a simple question. When you hit play on a video, do you think your device downloads the entire video file? Of course not. Modern streaming systems don't send one giant file. They send the video in tiny pieces, usually 2 to 10 seconds each, and switch quality on the fly. This is the foundation of streaming: segmentation, multiple resolution, adaptive bitrate. After transcoding is complete, we don't store a single video file. We store multiple versions of same video, which are like 1080p, 720p, 480p, etc. Each resolution is broken into small chunks. So as an example, for 1080p, the chunks will be stored in multiple, the video will be stored in multiple chunks, which is like 1080p slash chunk1.ts, 1080p slash chunk2.ts, so on. And we create manifest files like .m3u8 for HLS and then .mpd for text file. These files tell the player what resolutions exist, what the segments live, and how to switch between them. It's basically a roadmap for video playback. Here is what your player is doing every few seconds. It checks your network speed, it checks how much video is already buffered, and also it picks the best possible quality for the next segment. If your network is fast, it streams at video 1080p or 4K. If your network drops, it instantly switches down to 480p. No buffering, no freezing, just smooth playback. Now here is the part most people never think about. Your backend servers are not streaming the video. Almost everything is handled by the CDN, a global network of edge servers. So let's break that down. First, users will go to the actual edge CDN closest to the server. It serves the segment straightly from cache. If the edge node doesn't have the segment, the regional cache might have it. If both caches misses, it fetches from the origin. And it will hit S3 storage only when it is absolutely necessary. This layered caching strategy reduces latency, protects origin servers, it handles massive peak in traffic, and it makes streaming scalable globally. So, let me ask you, where do you think most popular video segments come from? The answer is CDN edge nodes, not the backend. Now, before the player goes to the CDN, it hits your streaming API. So basically, the request is from user to API gateway to streaming API to CDN. The streaming API service handles user authentication, age restrictions, geo restrictions, parameter unlisted, video access, issuing signed or tokenized URLs. Then it redirects the client to the CDN where the real streaming begins. This means your backend stays stateless, scalable, low cost, and protected from huge traffic spikes. In case of failure resilience and error handling, streaming must work even when things fail. At player side, if a segment fails, retry or at a lower resolution, automatically switch to another CDN POP. CDN side, if it fails, then fall back to regional cache. If regional cache fails, then fall back to origin, and if that also fails, then get the data directly from S3. And at server side, if there is any failure, then we can use multiple manifest, health check, or auto-scaling. This ensures high availability even during outages. Now, in terms of security and DRMs, video must be protected from piracy and unauthorized access. We can use tokenized URLs, sign-in URLs with expiry, geo-blocking, rate limiting, etc. In case of observability, to ensure streaming quality, the platform consistently measures startup time, rebuffering ratio, average bitrate, CDN cache hit ratio, segment download latency, etc. These metrics drive automated alerts, CDN routing adjustments, dynamic video quality improvement. So in summary, video streaming works like this. Video is split into the tiny segments across multiple resolutions. The player uses adaptive bitrate to choose the best quality for every segment. A global multi-layer CDN handles almost all delivery. The streaming API enforces rules and it returns signed URLs. Failover system handles outages. Security and DRM protect content. Observability ensures the platform maintains high video quality. This is how platforms like YouTube handle billions of video plays every single day smoothly, efficiently, and let's quickly dive into how YouTube handles massive live events like the Super Bowl or major sports final. First, we will look into live video ingestion. Broadcasters push their feed to distributed ingest servers. Multiple regions ensure redundancy and prevent single point of failure. Question for you. Do you think one server can handle millions of viewers? No, distribution is key. Now second, which is basically real-time transcoding and low-latency segments. The feed is transcoded live into multiple resolutions and bitrates. Segments are tiny, 1 to 2 seconds for low-latency playbacks, then manifest update continuously. This ensures smooth playbacks and adaptive bitrate switching. Third, multi-CDN and edge caching. Multiple CDNs serve the same video globally. Hot segments are cached at edge pops or for instant delivery. Failover automatically shifts traffic if one CDN or region goes down. Quick thought. This is how millions can watch a single goal or play simultaneously without buffering. Last one, which is a fourth, is which hits monitoring and security. Real-time metrics tracks buffering, latency, and segment delivery. Sign URLs and DRM ensure only authorized viewers can watch. And last thing, which is summary. So in short, distributed ingestion to real-time transcoding to low-latency segments, and from there it is multi-CDN edge caching to monitoring plus security. This combination allows YouTube to stream huge live events flawlessly anywhere in the world. So, and that wraps up our deep dive into designing a YouTube scale video platform. Let's quickly recap what we have covered. In today's video, we basically discuss about functional and non-functional requirement, APIs, high-level design, and deep dive. In deep dive, we discuss about video transcoding, video streaming, as well as live streaming for massive events. The key takeaway, building a platform like YouTube is all about scalability, reliability, and low latency, combined with intelligent orchestration across multiple layers, from storage, processing, caching to delivery. By breaking the system into modular components, you can scale each part independently, handle massive traffic, and provide a seamless experience to millions of users worldwide. From upload to transcoding to streaming, every part of the pipeline is carefully engineered to make watching videos fast, smooth, and reliable. And that's the magic behind every YouTube video you play. Thanks for watching. Don't forget to like, subscribe, and hit the bell if you enjoyed this system deep dive.